students, let's do lesson 7, hydrocarbon origins and processing. So we want to identify and describe significant organic compounds in daily life, and then describe in general terms the physical, chemical, and technological processes used to separate organic compounds. Okay, so as you know, we have all of these compounds here in our chart. We've got our hydrocarbons, our derivatives, our aromatics, and we want to know, where did all of these things come from? So let's take a look. Here, just take a look at this picture here. I want to focus on this. Okay, so you know that the sun sends energy to the earth, of course. Plants do photosynthesis. They take in CO2 and water and sunlight, and in the chloroplast of the plant with the chlorophyll, we make these products. So CO2 plus water plus energy produces glucose and oxygen. Okay. Now glucose is this molecule C6H12O6, which looks like this. And the leaves and the stem are made of a molecule called cellulose, C6H10O5. Anyway, these are carbohydrates, C's, H's, and O's. And of course, in our course here, we're talking about organic compounds that contain carbon. Okay, one thing I want to make you very clear on is, as photosynthesis happens and makes the molecule glucose, the energy that's stored in the glucose came from the sun. So energy, kilojoules, come from the sun, and they hit the plant, and as the plant brings in CO2 and H2O and makes glucose, that energy gets stored in the molecule. So all these bonds contain energy, stored energy. With that background, then we come to this diagram. Now, so we have these plants, and over time those plants die, of course. So here's this layer underneath the water. Here's that same layer. This black layer is the dead plants. Okay, so there's that layer. And then over thousands and thousands and millions of years, all these other layers build up. And this layer that was once a bunch of plants has now turned into coal. So let's take a look a little bit more closely how that happens. So here is a molecule inside our plant. Now, as it gets buried deeper and deeper under the ground, that molecule's in here somewhere, right? The ground heats it up from beneath because the Earth's core gives off heat energy, and all of these layers compress those molecules. So watch what happens here. We got heat heating it up from underneath. We got these layers of sediment building up on top of these molecules. These molecules get compressed, and of course you know that this takes millions of years, this compression and this heating, this slow cooking and this pressure. This molecule gets transformed into all of these other molecules, these hydrocarbons, and that's where our hydrocarbons come from. Notice the kilojoules that are in those molecules originally came from the sun. They're still trapped in those molecules, and those molecules have been changed into coal or crude oil. Coal is based on plants, crude oil is based on zooplankton. One thing I need you to understand about crude oil is that crude oil is just a mixture of a whole bunch of compounds. So short chains, longer chains, really long chains are all mixed together in this black soup that we call crude oil. Okay? But all of these molecules are inside of that crude oil. Okay, here's an example of a coal seam, a picture of a coal seam way under the ground. Okay, and so those molecules that have that energy stored in them, in this coal seam or in these crude oil pockets, we need to dig that out. So here's a coal mine. They dig a shaft, send an elevator down. Coal miners are working in there digging out the coal, and then we bring it back up here, and of course we burn it for energy. Okay, so let's talk about some of these hydrocarbons. So of course we have coal. Now, where do we get coal from? Well, how do we get coal? We extract it through surface mining. So here we're mining on the surface, or we have underground mining. You can see he's got a little remote control and he's operating this device that crushes up the coal. Physical processing involves crushing and grinding. We don't need any chemical processes. We just crush it, grind it up, put it on train cars or trucks, and we send it away. And then we burn it in coal-fired generating stations, and then we get electricity. Okay, so that's coal. There's also natural gas. Natural gas is a mixture of methane and ethane and propane and butane, depending on the source. Now, how do we get this out? Well, we drill these shafts, and then we frack, or we fracture the ground. So you can see these fracking zones, and then the gas seeps in through the cracks into our pipe, and we pump it out of the ground. I like this picture. It's a cool picture. Now, it's amazing that we can do this drilling where we go horizontally. Anyway, some of the processing we're going to talk about later. You'll see this tower a little later. It's called fractional distillation. We can separate natural gas into its components, and we'll talk about that a little bit later. Sometimes these mixtures also have some nasty chemicals in them, like hydrogen sulfide. It's a very nasty chemical. We use chemicals to remove hydrogen sulfide and CO2 from our natural gas. And natural gas is used as a heating source. So, like, for example, propane heats up barbecues. Okay. Crude oil and heavy oil. Again, we extract these from the ground through drilling. Sometimes we use pressure and water to get the chemicals out. Once again, we use fractional distillation, which I'll talk about in way more detail in a little bit. We have another process that cracks long chains into shorter chains, like you see here. And we use these molecules for gasoline, jet fuel, and then asphalt or tar shingles. Okay. And then, of course, we got the oil sands like we have up in northern Alberta. An oil sand is a particle of sand surrounded by water, surrounded by oil. That's an oil sand. Okay, so we can use steam and hot water injection to get this out of the ground and to separate the oil from the steam, separate the oil from the sand. We can also use fractional distillation and solvent extraction, which I'll explain a little bit later. Cracking is involved with these as well, and some of the uses are the same as crude oil. Okay, moving on. Now, really need to make sure you understand this. What we're going to talk about next is a physical process. It's not a chemical reaction. We're just going to use a physical process. So, fractional distillation, a process in which the components of crude oil are physically separated by means of their boiling points. Okay, so you'll see a better example in just a second, but here we have some crude oil. And remember, crude oil contains a whole bunch of different chains of hydrocarbons all mixed together in this soup. Okay, we put it in a furnace, we heat it up, and we send it into this tower. And I'll explain the tower in just a little bit. When crude oil is heated to 500 degrees Celsius, it vaporizes. As the vapors rise up the tower, they cool. When they cool below their boiling points, they condense and are collected. Okay, so watch this. Okay, this down here represents crude oil, that black tarry stuff. Now remember, inside the crude oil in liquid form are all of these different chains, and they're all mixed together in here. So these different colored dots represent all these molecules. Okay, now that is very similar. This crude oil is very similar to a cookie, I guess. The cookie contains all of these parts. There's butter in the cookie, there's eggs, there's sugar, there's flour, there might be some flavoring like vanilla, and it's all in the cookie. What we're going to try to do in this tower is separate all of these little parts out. So it'd be like going backwards with the cookie. If we could process this cookie somehow and get the butter back, get the eggs back and the sugar. Now we can't do that with a cookie because the cookie has been baked and there's been chemical changes. We're not getting eggs back in their original form. But these, we can use a physical process to separate them and get all the colors together, or get all of the molecules together. Now watch this, I'll explain that. Okay, so we take our crude oil mixture and we heat it up. We heat it up, it turns into a vapor or a gas. So now I've got vaporized crude oil. And that crude oil begins its process into this fractional distillation tower. Now there's these bubble caps in the tower, and the vapors begin to rise up the tower. Now as they rise, each section of the tower is held at a temperature that's a little cooler than the one below it. So watch what happens. As these vapors rise, they have condensation points. So the green ones, or longer chain ones, are condensing at 400. The yellow ones are condensing at 250, for an example. And the red ones are condensing at 100. The blue ones never do condense, they stay gas. And the black ones never really boil, they stayed liquid. Okay? So, we have now just separated all of the parts of that crude oil into their fractions. We've distilled them, we've boiled them and condensed them and basically purified them. Fractional distillation. Here's the fractions. Okay, so these ones that condense down here, they're longer chains, and these ones that condensed higher up are shorter chains. Okay, and these ones up here never did condense; they're still gases, like propane is a gas. Okay, oh, and the ones at the bottom, this is asphalt and tar. There's another physical process that does not involve chemical changes called solvent extraction. Now the best thing I can do to make this quick and easy here is to describe it like a sandbox. Let's say you've got salt in your sandbox and you want to get the salt out. What could you do? Well, you could selectively dissolve and separate the mixture. You could pour water in the sand. The water will dissolve the salt. The sand won't dissolve into the water. And then as the water drips through, you've now got salt water. You boil that salt water, the water evaporates or boils off, and you're left with salt. Okay, so we used a solvent, water, to extract the salt. That's solvent extraction. Okay, now we're going to talk about chemical processes. So once we have these long chain molecules, what can we do with them? What if we need shorter chains? Like what if shorter chains like propane or gasoline are in higher demand than really long chains that are like 20, 30 carbons long? Well, we can crack the longer ones into shorter ones. We can crack them with thermal means. We can use heat to crack them. We can use catalysts to crack them. And we can hydrocrack them using hydrogen. So let's take a look at those three examples. So here's a simple example of what cracking is. Cracking is simply breaking apart longer chains. So I break that chain, and it's random. We might have that carbon down there will break off as well, perhaps, and we would be left with this. So we had C7H16, we broke that into two propanes, and we were left over with a little bit of coal or carbon. Okay, so that's an example of cracking. So we might take heptane in the presence of heat and pressure and break it into these molecules. So a longer chain is broken into shorter chains. We could use a catalyst to break this C17 molecule into these two smaller chains and a carbon left over. We can use hydrocracking, where we add hydrogen to a molecule and break it into those two shorter chains. Lots of times you'll see hydrocarbon cracking represented this way. You'll have a long chain, and it'll break into an alkane and an alkene because our hydrogens must balance. We've got 16 hydrogens here. Let's see, 2, 4, 6, 8, 10, 12, 14. Yeah, 16 hydrogens here. So we need 16 for products. 2, 4, 6, 8, 10, 11, 12, 13, 14, 15, 16. We made an alkene and an alkane when we cracked this molecule. Okay, now we move on to one called catalytic reforming. This uses heat, very high pressure, and catalysts to convert straight chain molecules into aromatics. And we do that because aromatic molecules burn efficiently. So let's look at this. Here's our straight chain, and it was converted into an aromatic. It had a branch on it, and for the hydrogens to balance out, there was some excess hydrogen here. Okay, alkylation. Alkyl means branches, so this is the process of increasing the number of branches. Again, this molecule with the branches burns more efficiently than this molecule. So you can see what happened. We had this long chain, we busted a couple off, and we put them on as branches. That's called alkylation. Now let's talk about octane a little bit. Octane has 8 carbons in it. 1, 2, 3, 4, 5, 6, 7, 8. Now, just a straight chain of octane would look different. It would just be 8 carbons in a row. But this molecule here, 2,2,4-trimethylpentane, burns really well in engines, and it resists this thing called engine knock, or premature ignition and detonation. So this molecule, this pentane, but it has 3 extra carbons on it, so it's really an octane molecule, but the parent is pentane. This molecule burns great in engines. We give this an octane rating of 100. Now this is not octane, this is heptane. This is 7 carbons. We give this an octane rating of 0. An octane rating, like you see here, tells us how well a molecule burns compared to this perfect molecule, octane 100. Okay? It doesn't mean if it has a high octane rating that it is this molecule, it just burns like this molecule. Okay, so the octane rating of gasoline is measured in a test engine and is defined by comparison with the mixture of 2,2,4-trimethylpentane and heptane that would have the same anti-knocking capacity as the fuel under test. Okay, so we compare the molecules in gasoline to 2,2,4-trimethylpentane. Now, it does not mean it has 2,2,4-trimethylpentane in it, it simply means it burns like it. Anyway, octane 91, octane 89, octane 87. This is the one I use. I got an old car, I don't really care. Okay, so that's it for that lesson.